Our next example subsystem is that of an arm. Um, this could be an arm, um, really any type of a mechanism that pivots from a point. This is derived from Husky Robotics 2024 shooter for Crescendo, but simplified to service this example, and to be as a model for future arms for 3061 or any team. There's a number of like best practices and features highlighted within this subsystem. One is the use of a remote sensor to measure the angle of the arm as opposed to using the encoder built into the motor itself. Um, it's a AdvantageKit subsystem. We won't touch on that quite as much because we saw that with the previous example with the shooter. Um, it uses an interpolating double tree map to map distances to angles. We saw that feature in the context of the shooter, so we won't focus on that too much. It also uses a debouncer to determine if the arm is at the set point. Again, we've seen that before. Tunable numbers for manual control and testing. We've seen before simulation class to model the arm. We'll look at that a little bit because it is a different simulation class being an arm. And it provides some visualization features as opposed to what we saw with the velocity simulator, the velocity system sim for the shooter. We will dive more into the SysIdRoutine. We skipped over that with the shooter. I want to take a look at what that looks like here for the arm. And again, it's got a system check and fault reporter stuff that we've seen before as well. So let's dive right in. The ARM extend subsystem base, which is what we do for all of our subsystems with AdvantageKit, has a reference to its hardware specific IO object, and then has creates and holds on to a reference to its inputs class. Again, similar to what we did with the shooter, we do have testing mode as a tunable here, which we can set to true or false. And then in this case, we can manually control the voltage of the arm or set a target angle in degrees as well. So things that we only use in testing mode when bringing the mechanism up or when characterizing the mechanism, for example, to determine, hey, let's try different distances. What is the appropriate angle for the shot? Okay, great. Dial that in. Next distance, what's the appropriate angle? We can do that very, very efficiently. All right, so let's look at the SysIdRoutine a little bit more because we haven't talked about that really before. So SysID, SysID itself is a tool provided WPI-lib, which analyzes a bunch of data and helps you determine your feed forward constants for KS, KB, KA, KG, and it can even give you starting values for PI and D as well. But we use it pretty much just for the feed forward stuff and then tune the PID on our own. The SysIdRoutine is how you go about getting that data, which can then be fed into the SysID tool. And so we can see here that when we construct the SysIdRoutine, we need to configure how the characterization is going to be done. There's a lot of defaults, but they're all spelled out here just so we can kind of see what's going on. For SysID, there's both a dynamic and a quasi-static test that's part of the characterization. And so this configuration determines how those tests are run. So you can specify the ramp rate. By default, it's 1 volt per second. We've changed it here in this example to 0.5 volts per second. Why might you want to change it? Well, an arm can only move through so far, and maybe based on how long it takes it to move through its range of motion and what voltage is needed to make it move, 1 volt per second um, might not be enough, or it might be too much. And so we can change that. Basically, we want throughout the arm's point of motion, we want to be able to hit several different voltages before we get to the end of its range of motion. So we adjust the value accordingly there. The step voltage is when it goes from stopped, jumps right to that voltage. By default, it's 7 volts. For maybe that's too much or too little. So in this case, we said, oh, that's way too much for this arm. Again, this is just an example. 2 volts is what we want for that step voltage. By default, the test times out after 10 seconds. You can always stop it sooner with your controller. So we left that alone. And then you always need this here. This little arrow function, this lambda, where you write the sysid state. Sysid is going to be the tool that's going to be looking for this and expecting to find it in the log. One thing I should clarify is that we use the hoot logs from CTRE when we're doing sysid. So the hoot logs provide more or are updated more frequently or at higher rate. So we get better data out of the hoot logs than we would with our own logs generated through AdvantageKit. So we use hoot logs for our characterization with sysid, which is why here I'm calling signal logger, which is the Phoenix 6 class to write this string. And then here is basically, okay, we need to tell the sysid routine, how do you control my device? Oh, you call set angle motor voltage on the IO object, and you pass in the volts. There you go. Great. So that's how we build the sysid routine. So this constructs the sysid routine. We're going to see how we register it in just a moment. That's done in the constructor. So here's the constructor for our ARM subsystem. Takes a reference to the hardware-specific IO object. We save that in our instance variable. And here's how we register our sysid routine. So we used to do all of our sysid routines like in completely different projects. It was a pain to like redeploy and update and deal with different repositories. Now it's all it's all part of our code. And to make it easy to characterize different things, we use a chooser, much the same as what we would use with like different auto routines. So here we're getting a reference to the sysid routine chooser singleton. We're adding an option, we're calling it the ARM voltage, and we're passing a reference to that sysid routine. The sysid routine chooser class is a singleton class just to help us manage the sysid routines. This was a little bit more challenging than expected. But we do use a log dashboard chooser, just like we would for auto routines. So we can choose which sysid routine we want to run, meaning do we want to do it for the arm or the drive motors of the swerve drive train or for the shooter, whatever it happens to be. And the way we make this all work is that there's actually 4 commands for each subsystem that we need to run to get a full sysid log that we can then pass along to the sysid tool. I mentioned dynamic and quasi-static earlier. For each of those, there's also going forwards and going backwards. And so those are the 4 different commands. So when add option is invoked, like we just did in our subsystem, we add it to the sysid chooser, and we use the hash code of that string name, like ARM voltage, as our identifier. And then we have these 4 different maps. These maps map a hash code to a command. And we have a map for dynamic forward, dynamic reverse, quasi-static forward, quasi-static reverse. All have the same keys, the hash code of the name of the subsystem sysid routine, ARM voltage, and then different commands here. The way we get the command is we use the sysid routine that we built in the subsystem class, and then we get the command by saying either dynamic forward or reverse or quasi-static forward or reverse. So we put all of this in the map. Then later, these methods here, get dynamic forward, get dynamic reverse, get quasi-static forward, get quasi-static reverse. These methods are called based on different buttons being pressed down on our controller. We'll look at an example of that in just a second. But what it basically does is it determines what command should be called. And it does that by lazily constructing a select command, which is a specific type of command in WPIlib. where you actually pass it a map and a key, and it will return the command based on the key. So this is how we make all of this work. So we lazily construct this thing. And the reason why we lazily construct it is we want all the subsystems to be constructed first, and add everything to this map before we build this select command. So these different commands are going to be returned based on pressing certain buttons. So we can see that, for example, currently in the swerve drivetrain command factory. Don't think that's the best place for it. Should probably go in the cross subsystems one instead, because it's not really related only to the swerve drivetrain. But regardless, here's where we use our operator interface object to get whatever the trigger happens to be for dynamic forward, dynamic reverse, quasi-static forward, quasi-static reverse. While it's true, it will use the SysIdRoutine chooser, get the reference to the singleton, and then get the command for forward or reverse. We usually use like a Xbox controller for this, and you have to press a couple different buttons to run the characterization routine. We don't even have these triggers mapped to anything on our like competition operator interface at all, because we only use this for characterization. So that's how that works. All right, so that's the SysIdRoutine chooser. So we did a little bit of a deep dive into that. Let's jump back to ARM. So we've registered the SysIdRoutine. Here we do our fault reporter with our system check command, in this case for the ARM. We're not going to dive into that into a lot of detail because we saw that more with the shooter. Here's what periodic looks like. With all subsystems, we call update inputs on the IO object first. We pass our inputs object to that. We then log them by calling process inputs on the logger, just like always. Here's where we have our testing mode stuff. So if testing mode is 1 and the pivot angle is not 0, we will set the angle to whatever it is. Otherwise, if the manual control voltage is not 0, we'll set the angle motor voltage to whatever it is. Again, really useful for bringing a mechanism up for the first time. Like, hey, let's just apply a low voltage, make sure it moves through its range of motion. Okay, let's try setting different angles and start tuning our PID. Okay, now let's actually put this thing on the field and characterize it and say at different distances what are appropriate angles, whatever it happens to be. And then as always, the last thing we do in periodic is we invoke the record method on the log tracer so that we know how much time did we spend in this periodic method for the ARM in this case. All right, public methods. We have a set angle method here. Pretty straightforward. We have a isAngle at set point that uses the debouncer like we saw with the shooter. Here's our system check command where we're trying 4 different angles. We still have the dot and till decorator like we did with the shooter, so we stop as soon as there's a fault, and then at the end we always go back to our lower angle limit, like our low position. We set the angle, we wait a little bit, we check that it got there. We generate a fault as necessary to say if the angle is too high or too low. Again, if we're running our system check manually, which we still need to do, and we're having the arm go to different angles, visually, we might not notice if it's off by 2 degrees. But this code will notice if it exceeds our threshold, whatever that happens to be, 1.5 degrees, and report an error. So that's why these system checks are useful. All right, let's look at the constants, see if there's anything particularly interesting here. Very similar to what we saw with the shooter. You will notice that there is a CAN ID for the motor for the ARM, but also a CAN ID for the encoder. One of the things we'll see in the hardware-specific class is having an external encoder to help us get a better indication of exactly where the ARM is. So we have PID values here for the rotation. We have our feed forward values, KS, KG, KB, KA. All of these come through SysID. We are using Motion Magic. And so Motion Magic, or specifically Motion Magic Expo, is how we're controlling the position of this arm. So there's some additional values here for KV and KA for Motion Magic Expo. Cruise velocity of 0 means don't limit the cruise velocity. Just go as fast as you can based on all the other constraints. Current limits, whether the angle motor is inverted, the gear ratio. So we have an angle motor gear ratio, and then we have a sensor to mechanism ratio that is separately. We'll see why those are important and what those mean. It all has to do with the gear ratios between the motor and the external sensor, the encoder, and the mechanism itself. A magnet offset, which is important for our encoder, and some limits on terms of the rotation and whatnot. All right, cool. IO class. So very standard IO interface here. Here's the ARM IO inputs class, similar to the shooter, connected, currents, temperatures, voltages. We're not interested in velocity, we are interested in position. So what is the position in degrees? What is the reference? The closed loop ones, again, these are the same idea, but for performance reasons, this one will always be populated, whereas these two are only populated when we're tuning. We have our updates input method that we always have, and then two methods to control the voltage directly or to set a specific angle. So let's look at RMIO Talon FX. This is what we use with the CTRE devices. You'll notice that unlike most of our subsystems, we actually do have two classes that implement the RMIO interface, RMIO Talon FX and RMIO XRP. So we'll look at the XRP one in a moment, but this allows us, we can have the same ARM subsystem and either have it be based on CTRE devices, or in this case, the XRP little robot as well. All right, best practices here, general subsystem things. We're using Motion Magic Expo voltage to control the position of the arm. We'll see some specific things related to that configuration. We also have a voltage out request because sometimes we just want to give the arm a voltage and have it move. So we have two different ways of controlling the arm here. The status signals we care about are all here. We keep track of the reference angle on our own. We have a debouncer for connections. And we have a sim object like we had for the shooter, but this is an ARM system sim. So we'll look at that when we create it in just a moment. We have our config alert in case configuration fails, all the tunables for PID, feed forward values for KS, KG, KA, KV, values for Expo, KV, KA, and then also the magnet offset for the CANCoder that is part of the mechanism. So we do have the motor for the arm and the CANCoder to measure the position of the arm. The reason why you might want a separate CANCoder and not just use the encoder built in the arm is to get a more accurate measurement. And also we want to use the accurate because it's like closer to the actual mechanism's rotation in terms of like some backlash you might have within your gearbox. But also it allows you to use like the absolute position. And what I mean by that is if the encoder is mounted directly to, let's say, the shaft that rotates the arm, then you know where the arm is in terms of an absolute sense as well with a CANCoder. In this case, that's not exactly what we have. There is a 4-to-1 gear ratio in this example between where the CANCoder is and where the arm pivot actually is, but it still allows us, given the limited range of this arm, we still know from an absolute perspective exactly where the arm is as well. This is useful because we don't have to zero everything out when the robot boots, meaning you don't have to have the arm in a known, let's say, down position when you turn on the robot, when everything gets zeroed, or have a command that zeroes everything. As long as the arm is within its range of motion within those 90 degrees or slightly less, wherever the arm happens to be, it will know where it's starting from. In crescendo, this is very important because we don't want the arm well, we don't want to have complicated field setup procedures. We want to be able to position the shooter where we want it for the initial shot, have it know where it's not without having to worry about making sure the things were zeroed properly when the robot was turned on or some other procedure. So some reasonings for why you might want an external encoder. All right, we create the motor, we create the encoder, we create our two different requests, we create get all of our status signals from the motor. Again, just like we did with the shooter, we register all those status signals here. They will be refreshed as part of all the other status signals. We won't call refresh within this code. We'll configure the angle motor and the encoder together. Let's look at what that looks like. So here's the CANCoder configuration. Direction, magnet offset, all of that type of stuff. We do have an apply and check configuration that works with the CANCoder as well. Here's where we're configuring the angle motor, all the current limit stuff. We want it in brake mode. Here's all the PID. Here's all the feed forward stuff. Here's all the motion magic stuff, inverted things. We have some software limit switches here. So we want to make sure that the shooter doesn't try to go too far down or go too far up, or the arm, rather. And this ensures that's the case without having hardware limit switches. Here's how we use the external sensor. So this is all part of the config object under feedback. So we specify the CAN ID of the remote sensor, and that's the angle encoder. There's a couple different ways to do it. We're going to fuse the CANCoder with the encoder inside of the Talon FX. And that's generally the best approach to pick. We do need to specify the sensor to mechanism ratio. So this is what is the ratio between the CANCoder sensor and the actual arm. And that's that 4:1 ratio. We will also specify what is the gear ratio between the motor's rotor and the sensor. Okay, this goes through the gearbox. And in this case, that's 45:1. So we specify both of those gear ratios. We then apply and check the configuration for the motor, register both the motor and the CANCoder with the fault reporter so that when the robot is disabled, it will periodically check to make sure those devices haven't generated any faults that might be problematic. All right. Different sim object. We're creating a new ARM system sim. Similar in many ways to what we saw with the velocity system sim. An ARM system sim is a little bit more sophisticated. So let's actually look at this class and see what it does. But the idea here is this ARM system sim object can be used to be the physics model for any ARM. And the way this is written, there's actually two constructors that are overloaded. So you can either have an external sensor like we do in this example here, which would be this constructor, or not, in which case you have this constructor. Either way is fine. But what this does basically is it gets the sim state from the CTRE device, deals with all the orientation stuff, deals with having an external encoder or not, all the gear ratios. The physics model is a single jointed arm sim from WPIlib. We model that with the overall gear ratios. We estimate the moment of inertia, assuming it's just like a rod, good enough. Min angle, max angle, the length, all of that. The other interesting thing here that we didn't see with the shooter simulation, the velocity system sim, is that this also has a visualization component. So we actually create a logged mechanism 2D for the arm. And we put the arm on a little bit of a tower here to make it easier to see. We add in the arm, we set it to blue. We set the tower to blue and the arm to yellow. And this way, as the arm moves, we can see this visually in the 3D view in Advantage Scope, which is great. In Update Sim, which we only do if we are in simulation, We will set the supply voltage on the sim state from the CTRE objects for the motor and the encoder. We get the voltage from the motor, pass that into our physics model, which is the ARM, single jointed ARM sim. So we do that. We update the model, get all the values out of the model, do all the conversions for all the things, and then tells the CTRE sim state, hey, here's your new position, here's your new velocity. Hey, in external encoder, if we have it, here's your position and velocity as well. And then we actually log the mechanism 2D for the arm, which provides that visualization once we actually update the arm with the new angle. So we get visualization with this object as well. So again, rather than putting all of this code inside of ARM.io Talon FX, we have a separate class that we can use for any type of an ARM simulation instead, which makes this a lot less busy. All right. Back to ARM.io Talon FX, update inputs. Again, we use the debouncer for connected. We talked about that with the shooter. Here's where we're getting all the status signal things. Again, we're not calling update all because it's already been updated. Only if we're in tuning mode are we grabbing the closed loop things. And again, with our tunables, if any of these tunables have changed, we have to update all of our stuff. Similarly, if we change the encoder magnet offset as well. And then the very last thing we do inside a periodic is updating the sim object. All right, we had a couple methods we had to implement. Set angle, which is an angle motor position request with the given position. And then we remember what that reference is. And then, or we can just use the angle motor voltage request to set the specific voltage. So Motion Magic Expo, it's a little, as we see, it's, there's more to configure, and you've got to tune it, and you got to get the right Ka and Kv values and all of those things. But once you do that, using it is super simple. We just, invoke the with position method on the request object for Motion Magic Expo voltage and pass in the angle, and we're done. Very simple. So, all right. What's unique about the ARM subsystem in 3061 lib is there's a second class that implements the ARM.io interface, and that's ARM.io XRP. It's a little bit simpler. So the XRP has a servo. This creates a new servo object. We do keep track of the reference angle. For update inputs, most of that stuff we can't get. So we can't update the current and the temperature and all these things, but we can get the angle of the servo. And we can pass along what the reference is. And we can support the set angle method, and we can't support the set voltage method. So if it's called, we just won't do anything. But we can support set angle. And so here's an example of a simple ARM subsystem for the XRP. All right, that is our ARM example subsystem.